the lessons. Okay, so last time we looked at the standing waves in strings. Okay, so when you vibrate the string produces a sound. That sound comes to you as a set of frequencies, not only one frequency. It's a combination of frequencies. We said the harmonics, right? Now we look at standing waves in a pipe. Think of this like an empty bottle. If you take an empty bottle with one open end and you blow over the top of the bottle. When you blow over the top, then you will hear sound. A sound is produced. Okay, same as you see, you may have seen people like they take a wine glass and then they rub their fingers, right? They rub their fingers on the tip of the wine glass. Okay, if they put a little bit of water, then they rub it and then they can produce sound, right? So how is all this produced? These are all based on stationary waves as well, but it is stationary waves in closed pipe. So one end is closed, the other end is open. Okay, now, or it can be like organ pipe, or it can be like a vuvuzela. If you know what is a vuvuzela, it's something like this. This one, This is like a some people they use it for parties, some people they use it for celebrations. Okay, all kinds of purposes. Okay, so it's like when you blow one end and then it produces sound, right? The sound is, the other end is open. The part where you blow, right, is the closed end, and the part where it's open, okay, that is the open end. So this also produces a closed pipe. Okay, so one is closed, one is open. So we will first look at closed pipe, and then only we look at open pipes. Okay, pipe with both ends open. Okay, so just to give you a general idea, all these are the principle of standing waves. So how is it produced in the closed pipe? Okay, let's go back to this one. Okay, how does it produce? Let me draw something like this. Okay, this is the pipe. Now, think of it as like one single particle. When I blow air across it, what happened to the particle here at the open end? The particle here, because it is open end, right? So they are free to vibrate up and down, left and right. Okay, they are free to vibrate. So since they are free to vibrate, we say that there's a freedom of motion. Okay, freedom of motion. So if there is a freedom of motion, then it can never be a note. It is always an antinote. So this is where antinote is formed. Okay, and the particle at the other end, the closed end, here all the particle vibrate left and right, like this. And then the particle here, as it tries to vibrate, okay, it will hit the wall. It will hit the wall and it is not able to vibrate. So it will stay stationary here. It has no freedom of motion. No freedom of motion. And thus we say this create a note here. Okay, so every time where there's a closed end, it will form a note. And every time there's an open end, it will form a antinote. What is note and antinote? It's just interference, right? Antinote is the constructive and note is the destructive interference. Okay, now, when the wave travels, when the particle get disturbed, when you blow air, right, the particle get disturbed, and then there's a wave traveling to the closed end of the pipe. And when it hit the wall, it got reflected. Now, in the case of the vuvuzela, when you blow one end, it's like this end you blow. This is open here, right, on the right side. The left side is closed end. It's like you blow here. Here, again, it creates a note. A note is created here because when you blow here, your mouth creates a closed pipe. Okay, the closed end. And over here is open. Now, in this case, right, when you blow, it creates a disturbance. that travels to the open end. But what happened to the wave here as it reached the open end? Now, I want you to know that even though it is open, right, still there will be reflection of the wave, okay? Because there is a difference in the density of the air inside the pipe and also outside the pipe. Inside the pipe, the air we say it is denser. Inside is denser and outside is less dense. Another word for less dense would be rarer. Okay, we said the outside is rarer medium and inside is denser medium. Okay, so inside, what happens to the molecule inside the pipe? Usually the molecule, they barely move. They barely move because they are stuck inside. Okay, so this creates a different density inside and outside. Outside is like open space. Particles are free to move like this. Okay, so when the wave travel to the boundary, you have to imagine like something like a boundary. Okay, even though it's not physical boundary, it's an imaginary boundary here. When the wave hit here, some of the wave will be reflected. Not many, not much, only a bit, maybe like 20%, they got reflected. The 80% will continue to travel and go out the pipe like this. Okay, so the thing is, I want you to know is that the particle denser, as they try to escape to the less dense medium, some of the particle will get reflected back. Okay, denser, because denser particle means they are heavier, right? They are heavier, and less dense means they're lighter. Lighter and there are more particles. You can think of it like you have a medium-sized ball that hit a small ball, right? Maybe in some cases it would follow the ball and move to the right, and in some cases it would maybe like knock back a bit. Okay, sometimes it would knock back a bit. Okay, so same as the wave. So as the denser particle collide with the less dense particle, some of the particle they will knock back. Okay, they will knock back. So there will be a reflection of wave in the medium. Sorry, in the boundary, this imaginary boundary here. Okay, so both end, regardless, closed end or open end, reflection will occur. Okay, reflection will occur. All right, so now we know that the reflection occurs, then the wave will interfere. Again, you get standing waves. Huh? You get standing waves. Now the wave here, we represent it as transverse, but in the actual case, it is longitudinal because we are dealing with what? We are dealing with sound wave. Huh? So they vibrate, all the particles inside, they vibrate left, right. Left, right, left, right. But we represent it as transverse, like this. Okay. What are the patterns that will form in the closed pipe? Okay, we draw like a wave, a normal wave. Okay, we do like this. To find out the pattern, okay, the harmonics, just like the strings, we just find how many waves can fit between a note and an antinote. Okay, so we start with a note. This is a note. What is the next antinote? Next antinote is on the crest here, right? So until here, that is you get the first pattern. Okay, so your first pattern is this one. One end closed, one end opened, you get this pattern. Okay, different from the strings. The strings is two note, right? This one is only one note, one antinote. Okay, now this one we call it what? Fundamental mode, or the first harmonic. Okay, what is the wavelength? Wavelength, length equals to, this is only 1/4, right? From here to here, only 1/4 of the wave. So it's 1/4 of lambda. Lambda is 4L. And take the frequency, V over lambda, V over 4L. This is the fundamental frequency. Let me box this. Okay, fundamental frequency. Fundamental mode is the one with the highest amplitude. You hear this one the loudest. Okay, you hear this one the loudest. Now, what is the next wave that you may hear? The next one, okay, you go to the next antinode over here, and this is one loop and half a loop. Okay, so one loop. There's a note in the middle, right? So one looped and then half a loop. Half a loop, one loop. Okay, you get something like this. And this is the second harmonic. L equals to, how much is this? How many waves? 3/4 of lambda. Okay, because if two loops, then is one whole cycle. This is 1.5, so it's 3/4 lambda. Lambda equals to 4L over 3. Frequency, we put in the frequency V over 3V over 4L. And we can write this as 3 F0. This is my second harmonic. Third harmonic. Okay, next antinode is over here. This is 2 loop and a half. So 2 note in between. You get 2 loops and then half. Like this. Third harmonic. Length equals to, how many lambda is this? This is one cycle is until here. And this is half a cycle. Sorry, a quarter of a cycle. Not half, a quarter. A quarter like 1/4. So this is 1, right? So 4 over 4 plus 1 over 4, we get 5 over 4. Lambda. And lambda equals to 4L over 5. Frequency equals to V over 4L over 5. That is 5V over 4L. It's 5 times of the fundamental. Okay. Now, just do one more, the last one, the fourth harmonic. So amplitude is the next one. 3 loops and half a loop, right? 3 loop means 3 note. 2, 3, half. 1, 2, 3, half. Okay. The fourth harmonic, length equals to, you can already see the pattern, right? This one is F note, this one is 3, 5, this should be 7. L equals to 7 over 4 lambda. 4L over 7. So frequency equals to 7V over 4L. So the frequency of the fourth harmonic is 7 times of the fundamental frequency. All right. All this come at the same time. When you blow the bottle, all this form. Okay, but the loudest is the first one. If you want to hear the second harmonic or the third harmonic louder, then you have to adjust the length. Okay, adjust the length. Okay, now what do we get here? What do we hear when you blow? Then you hear this odd numbers frequencies. You hear 1 F0, you hear 3 F0, 5 F0, and 7 F0, and this keeps going on. 7, 9, 11, okay, all this. Okay, so you get a series of +2, +2, +2. In other words, they are the odd frequencies. Where is the even frequencies? You cannot hear the even frequencies. Okay, you can't hear it with the closed end pipe. So we can say that the N harmonic the nth harmonic is equals to, okay, this is 2n minus 1 F note. Okay, if I want to hear, for example, the 20th harmonic, I put in 20 here, then I get how many times the fundamental frequency. Okay, so this one is the kind of like the general form, the general equations lah. Okay, that is for the standing waves of a closed pipe. We can take a screenshot and I will go to the next slide. Okay, so doesn't really matter if the air is inserted here, there will be a reflection, standing wave will form. If air is inserted here, again, there will be a reflection at the open end and a standing wave will form as well. Okay, next one, we will look at the standing waves in open pipe. Now, for open pipe, how is it different from closed one? Open pipe is like a flute. Okay, the instrument's flute, where you blow at the side. You blow from the side, right? The both ends are open. You blow from the side. So look something like this. If I draw the pipe, this is the air column. So I got two open ends. And let's say the air insertion is at the middle here. Now, if I blow from here, then what happened to the particle here? Let's see. The particle at both ends are open, right? So they are free to vibrate left and right. Left and right. There is a freedom of motion, so there will be antinode, antinode. So we already have two antinodes at the end. Now, this particle, the particle next to it also vibrate left and right because they are longitudinal wave, right? So longitudinal wave parallel to the propagation of waves. Okay, left and right, left and right. So if all the nearby particles vibrate left and right, then what happened to the particle in the middle? Particle in the middle cannot move anywhere because they go all left and right, left and right. This one is like what? Like pushed at the center. Okay, cannot move left, either left or right. So this will create there's no freedom of motion. This will create a node at the center of the pipe. Okay, so here we got two antinodes and one node at the middle. That gives us the first pattern, the fundamental mode. Can you draw the fundamental mode? Okay, here is our wave. Again, we use the how many waves can fit between antinode and the next antinode. Okay, so meaning that we start from an antinode, the crest here. Let me draw a line. We throw out this part. Okay, we start here. Where is the next antinode? Down here. This is the next antinode. So we draw the pattern like this. Okay, so the first pattern for an open pipe looks like this, like an hourglass. Okay, one node at the middle, antinode, antinode, fundamental mode. First harmonic. The length of the tube is equals to, okay, how many wavelength is this? This is crest, C, to trough, T. Crest to trough is half a wave. Okay, crest to crest is one wave. So if crest to trough, that is half a wave. So lambda divided by 2, lambda is equals to 2L. Frequency, V over lambda. V over 2L. So this is different from the closed pipe, right? Closed pipe is V over 4L. This open pipe is V over 2L. Okay, second, how many waves can fit between the first antinode and the next one? So this is one cycle, right? From here, one cycle. Then we have two nodes at the center. One cycle. And this is one cycle. Trough to trough, crest to crest. Okay. Second harmonic, length equals to lambda. Same, huh? So frequency equals to V over lambda. I can write this as 2V over 2 lambda, and that is 2 F node. You can see this is similar to the standing waves in strings. Okay, strings is also same. Huh? The fundamental frequency V over 2L and 2 F node here. Two more here. Antinode. Extend this one. So 3 loops, 1, 2, 3, and half a loop. 3 loops means I have 3 nodes at the center. 1, 2, 3. So something like this. Okay. Sorry, not 3 loops. 2 loops at the center, and then half a loop at both ends, right? So 2 loops at the center, half loop at both ends. Third harmonic, length equals to, from where to where is one wavelength? From here to here, crest to crest. This is 1 lambda. Okay, how about this one? From here to here. Trough, crest, crest to trough. That is half lambda. Okay, half lambda. So this is 1 plus 1 over 2. It's 3 over 2. 3 over 2 lambda. Lambda is 2L over 3. And frequency is 3V over 2L. 3 times of fundamental. Box this. And the last one, you can already go by yourself. We got 4 nodes at the center. 1, 2, 3, 4. Okay, so fourth harmonic length is 2 lambda, and frequency is equals to 2V over L. Okay, we change it. We have 4 times V over 2L, and that is 4 times of the fundamental. In the open pipe, what I'm hearing here is all the harmonics, the integral, multiple, 1 F note, 2 F note, 3 F note, 4 F note. All of this I'm hearing. The even numbers and the odd numbers I'm also hearing. What is the pattern for N harmonic? For N harmonic, let's say I want to find the 30th harmonics, then I just put N F note. This is same as the strings, the guitar strings. Okay. Now, how is it different in terms of like the sound from the open pipe and the closed pipe? The closed pipe, right, you're only hearing the odd frequencies, but the open pipe, you're hearing all of the frequencies. So there will be a difference in the sweetness of the sound. Okay, you'll find that the open pipe will have a sweeter sound simply because it contains all of the frequencies. Okay, but For the closed one, some frequencies are missing. The even one, they are missing. So if you compare the sound between these two, the one that has the open end will give you a sweeter sound, right? So like the flute. Okay, there are some instruments that you can change. You can cover the one end and then you can open both ends. Okay, these are like you can change from a closed pipe to an open pipe so that you get to change all the frequencies that you want. Okay, you want the odd one or you want the even one. So that is for the standing waves for the pipe. For the pipe. Now, usually questions they'll ask you how to get what is the frequencies. Okay, calculate the one that I boxed here is the one that you may need to take note. Okay, 4 times and find the velocity, all that. Find the velocity, find the wavelength, find the frequencies. Okay, take a screenshot of this. And for the next part, I will go to I'm going to talk about the end correction, the end corrections. Okay, so end correction. Now, what is end correction? For all the cases that we talk about, okay, for the open pipe, for the pipes, just now, we assume that the antinode form exactly at the open end, exactly at the mouth of the tube. But in the actual case, the antinode is slightly further outside. Okay, if I draw the pipe, this is, okay, let's take one closed pipe. Here we have node, antinode, we assume it to be here, right? For all the calculations just now, we assume that there is no end correction. Now, in the actual case, the antinode will form slightly further out because here is actually the actual point of reflection, meaning that the wave travels out a certain distance, then only it got reflected. It's never like perfectly at the mouth here. Okay, it went slightly past the opening. So if you measure the actual position of the antinode, which is outside here, and from the mouth of the tube, we call this end corrections. Okay, it is length. It's measured in length, in meter. Okay, so this is end correction, and here is the length of the pipe. A closed pipe has one end correction because only one end is open. Okay, now for an open pipe, by closed I mean like one end closed. Okay, you can have both end closed pipe also. Both end closed, in that case it would be 2 nodes at both ends, just like the string lah. Okay, and for closed pipe, like all closed, there's no end correction because there's no open space, right? But for these open pipes, if you have 2 open end, then you got 2 end corrections. At the center, you have node, antinode outside here, and another antinode outside here. Okay, so here I would take C, and then here is another C. You got 2C plus the length of the tube L. Then we have to do a little bit of adjustment to our formula, right? Our derivations. So previously we wrote like L equals to, for the closed pipe, we write L equals to 1 over 4, right? 1 over 4 lambda. Lambda over 4. That is if I do not consider the end corrections. But if I consider the end corrections, then I have to write L plus the end correction, then only equals to lambda divided by 4. Okay, so this one, I do a little bit of rearrangement. I get lambda equals to 4L plus C. Let me box this. This one is for us to find the lambda, okay, considering the end correction is there. Now, how about for the open tube? For the open tube, we do the same, but this one, L, we plus, there are two end correction, right? We plus 2C and equals to, what is this? The fundamental mode for the open pipe. This is lambda over 2. Okay, the first pattern, the fundamental mode. So lambda equals to 2L plus 2C. Okay, so this two we use to find lambda. Given the end correction, you have to know the end correction to use this to find it. Now, how to find the end correction then? The end correction, it is discovered experimentally to be 0.6 times the radius of the tube, considering that your tube is cylindrical. Okay, if your tube is cylindrical, which most tubes are, then we take the radius, you times by 0.6, then you get the roughly an estimate the end correction for the pipe. Okay, you can calculate that way. Usually they will give you diameter, you get the radius times 0.6, you get the C. Okay, C is equals to 0.6 R. Now, if the end correction is given, you can use this to calculate the wavelength of the standing waves. Now, in some cases, the end correction is not given, and they use another method to find the lambda, okay, without knowing the end correction. So what they use is they use an experiment that they call the resonance tube experiment. Okay, the resonance tube experiment. Now, let me draw a little bit of setup for this experiment. So basically you have a tube. You have a tube closed end. The other end is opened, okay, one closed end. And then it connects to a hose to a funnel here. And all this is, they are filled with water. And this funnel, you can adjust the height of the funnel. You can bring it up, down. The water level here, this water level can be adjusted by adjusting the height of the funnel. If you raise the funnel up, then the height will increase. You drop the funnel, then the height, water level will decrease because of the pressure stuff. Okay, so the point is you can change the water level here. Okay, now here I take a tuning fork. What is a tuning fork? The looks like a fork lah. When you strike it, right, it will give a monotone, a mono frequency. There's only one frequency. People use it to tune the instrument, right? They tune the instruments. So this one, you have to know the frequency of the tuning fork. And usually it's given. They will say that, okay, this tuning fork is like 512 hertz. Okay, and they strike the tuning fork, they let it vibrate at the mouth of the tube. What will happen here? Why do we use water? Why do we use water here? Now, as the tuning fork vibrate, right, it will create longitudinal wave, right? That longitudinal wave travels to the water. Water is a lot denser than air, a lot denser. So as the wave hit the water, it got reflected back. Okay, you can think of it like you go less dense, suddenly you go denser. It's like you're hitting a wall, okay, for the wave. Okay, for the wave. It's like a small ball hit a large ball. This is rarer and this is denser. Okay, when it hit the large ball and it bounced back. So when the wave hit the water, it bounced back. Okay, bounce back. And again, bounce back, you get a interference. Okay, huh? Now the idea behind this experiment is that they start at a random height, okay, whatever height they want to start, and then slowly they will decrease the height, the level, the water level. Okay, they will decrease this water level by adjusting the funnel here. Okay, so how the experiment is conducted: first, they vibrate the tuning fork, place it over the top, and then they slowly decrease the water level until they hear a loud sound. When they hear a loud sound, what does it mean? That means resonance is happening, and resonance is due to standing waves. Okay, so meaning that when they hear the resonance, when they hear loud sound, then okay, that is the fundamental mode. That is the first resonance. Okay, the first pattern. Now they take the length. Once they hear the loud sound, write down the length. Okay, the length. What length is that? The length is from the water to the opening. Okay, from the water to the opening, the mouth of the tube. So they name it L1. Okay, now let me write this down here. First resonance. L1 plus C. Okay, L1 is the first resonance they calculate, and then they form an equation L1 plus C, the n correction, and then equals to lambda over 4. That is equation 1. Okay, and then they continue. After they hear the first loud sound, they continue to lower the water. Okay, by lowering the water, meaning that you're increasing the length of the tube, right? Until the second resonance occur, the second loud sound. Okay, then they mark again the length L2 plus the n correction equals to the second resonance is what? The second pattern, right? The second pattern for the closed pipe is 3 lambda over 4. Okay, 0.75 lambda. This is equation number 2. Okay, now once they got these two, then they do a little bit of mathematics. Okay, equation number 2 minus equation number 1. We get this L2 minus L1. The C got cancelled out, right? So we don't need to know the C. We got cancelled out. 3 lambda over 4 minus lambda over 4. That becomes 2 lambda over 4. 2, 1, 2, 2, 2, 4. L2 minus L1 equals to lambda over 2. So lambda equals to 2 L2 minus L1. And this is, take note of this. This, I can calculate the wavelength just by knowing what is L2 and L1. Okay, here I need the n correction, but here I do it experimentally. I find the L2, L1, I can get the lambda. Okay, because there's no n correction in the equation. Okay, so lambda is this one. Then I can also calculate the speed. V equals to F lambda. So meaning that V equals to this one, you add F inside. 2F L2 minus L1. Like this. Okay, 2F L2 minus L1. Now the thing is, when you get the velocity, this is velocity of what? Of the progressive wave, right? Of the progressive waves that forms the standing waves. Okay, the reflected waves and the traveling waves. And this is velocity is at whatever temperature you are conducting this experiment. Okay, whatever temperature. So this V is, we name it as V theta. V theta is the theta of the temperature of the surrounding. Okay. Now, sometimes in the question, they want you to find the velocity of the wave, of the sound wave at ice point. Okay, at ice points. So velocity at ice point V naught. Okay, it can be given in the equation V naught over V theta equals to square root 273 over 273 plus theta in degrees Celsius. Okay, so let's say you conduct this experiment at 20 degrees Celsius. You calculate the velocity, that is the velocity at 20 degrees Celsius. You want to convert it to the velocity at ice point, V naught. Okay, because sound velocity, the speed of sound is different in different temperatures. Okay, so example. Let me give you one example. Okay, a student conduct the experiment. He takes a tuning fork of 300 hertz, place it over the top, and then he hears the resonance. He calculated the length, and the shortest length of the column, shortest column is 0.28 meter. And then he continues to lower the water level. He hears the next one. Next one is at 0.84 meter. Considering he's doing the experiment at room temperature about 20 degrees Celsius, find the velocity V naught at ice point. Okay, so we want to find a velocity, right? Meaning that we will use this equation. Okay, so V equals to 300, and then L2 minus L1. L2 is always bigger than L1. L2 bigger than L1. Okay, so 0.84 minus 0.28. Okay, you can calculate this. What is this? This is my V theta, right? V theta. Okay, then I convert it to ice point. V naught equals to 273 over 273 plus 20 times into whatever answer that you get from here. You go here. You get the V naught. Okay, so there's about like 24.3 meter per second. That is the velocity of the sound wave that is producing at the tuning fork. Now, what if the question asks about the end correction? End correction. They ask you to calculate, okay, what is the end correction of the tube? Then we need another formula, okay, because this one we don't have a C inside, right? We cannot calculate it. We need another formula. The thing is, here, okay, how do I phrase this? Wait. Okay, we will take equation 1, divide it by equation 2, we get L1 plus C over L2 plus C. And if you divide this one, right, the 4 cross out, the lambda cross out, you get 1 over 3. Simplify, 3L1 plus 3C, L2 plus C. And 2C equals to L2 minus 3L1, and C equals to half L2 minus 3L1. And this is my equation for the end correction. Again, L2 bigger than L1 here. Now, sometimes the question will ask, is this the first resonance or is it the second resonance? How do we know? Because when you do the experiment, the sound that you hear, the loud sound, the resonance, you're not sure which one. It could be the first one, it could be the second one, it could be the third one, right? It could be any harmonics, it could be the second harmonic. Not necessarily it is the fundamental mode. Maybe you're hearing the second harmonic. Okay, you won't know. You don't know. You just hear a loud sound, right? But how do we know? How do we determine whether it is the first resonance or not the first one? Now, you see, I get this equation, the end correction equation, by assuming that the first resonance is the fundamental mode, right? Because I take this equation and also I take this equation. I arrive at the equation here, C. This is based on the assumption that the first resonance is the fundamental. That's why I put lambda over 4 here. Now, in some case, the first resonance can be the first harmonic, sorry, can be the second harmonic, or it can be the third harmonic, right? So that gives you another equation for the end correction. You see, here, I draw a line. Let me put this. If the sound that I hear, the first loud sound, is the second harmonic, that means this one, 3 pi over 4. Okay, meaning that I would call my length 1 plus C equals to 3 pi over 4. Because that's the first sound I hear. Okay, let's just say that the first sound that I hear is the resonance of the second harmonic. Okay, okay, stick with me. Later I'll give you some examples. All right, so L1 plus C equals to 3 lambda over 4. And then the second one, I lower the water level. I hear another loud sound. Okay, that could be L2. That could be the next harmonics, which is 5 lambda over 4. Okay, 5 lambda over 4. Okay, let me move this a bit. All right. Now from here, 1, 2, again, I take 1 divided by 2. Okay, so I get what? Equals to L1 plus C over L2 plus C. This one, when I divide it, I get 3 lambda cross lambda, 4 and cross 4, I get 3 over 5. Okay, 3 over 5. And then, okay, simplify. 5L1 plus 5C equals to 3L2 plus 3C. Minus 2C equals to 3L2 minus 5L1. Okay, and then I move the 2 again, I get 1/2 3L2 minus 5L1. Another equation for the end correction. Why I got 2? The first one is based on the assumption that the first position of resonance is the fundamental. That's why I take these 2 equations. The second one is the end correction if the first position is the next one, right? The second harmonic, not the fundamental. Okay, this is pattern 2 and pattern 3. The first one is pattern 1 and pattern 2. Okay, pattern 1 and pattern 2, this one is pattern 2 and pattern 3. Which is why sometimes when you calculate the end correction, you get a negative value. Because by right, the end correction should be a positive. It should be outside the tube. If you get a negative, that means that it is inside the tube. Okay, that's not the case. It should be outside the tube. So meaning that if you get a negative, that means, let's say you calculate, you get this one is negative. Okay, you use the first equation. You get this negative, like negative 0.05. That means that the first position of resonance is not the fundamental mode. Okay, because here the end correction you get a negative, it's not valid. Okay, then you will use the next equation, which is this one down here. You recalculate the end correction, and if you get a positive value like positive 0.05, then you know, okay, this is the end correction. It's outside the tube, it's a positive values. And what is the first position of resonance? This one is 3 lambda over 4, not lambda over 4. That means this is actually the first resonance that you hear. The first sound that you hear is actually the 3 lambda over 4. Okay, not the lambda over 4. All right, now let me give you one example. I'm going to clear the top left. If you want to snap, you can snap now. I'm going to clear the top left, get some space. Okay, wait. Okay, I think I'll just clear the bottom. This one. Okay. Okay, example. The same student takes the vibrating tuning fork. This time he uses another vibrating fork that has a frequency of 512 Hertz. He put it over the top and resonance is obtained. Resonance is obtained. Now, the question here did not specify, is it the first resonance or what? Okay, it just says that the resonance is obtained. Okay, it could be the fundamental mode, it could be the first, second, or third harmonic. All right, so resonance is obtained, and then when the length, he found that it is obtained when the length is 0.5 and 0.84 meter. Okay, find the end correction and also find what is the first position of resonance. Okay, first position. What is the first pattern that you hear? All right, then we use, okay, the first one, we try the first one. C equals to half L2 minus 3 L1. Remember, L2 bigger than L1, so 0.84 minus 3 and then 0.50. What do we get? You calculate this, you get negative, right? You get negative 0.33. What does it mean? Meaning that the first resonance is not the fundamental. Okay, so that is why you get negative here. So we then use the second, C equals to half 3L2 minus 5L1. Okay, so this is based on the assumption that it is the 3 pi over 4, and the next one is 5 pi over 4, right? We calculate again, the same value goes in, 3 times 0.84 minus 5 times 0.50. Okay, we calculate this, you get positive 0.01 meter. Which one is the answer? This one is the answer. The end correction is 0.01 meter. And what is the comment on this experiment, on this calculation? What is your comment? What is the conclusion? It says that the first position of resonance is actually the length of the 3 lambda over 4. It is not the fundamental mode. 3 lambda over 4 is the second harmonic. Okay. So if this one also you get negative, then you go to the next one, to the 1 and 2, 2 and 3, and 3 and 4, 4 and 5.